All right, so we're taking our conversation regarding aromaticity. So we know how to name aromatic molecules. So then what I need to emphasize here to start the discussion is that benzene is unusually stable. And you can tell that it is unusually stable a couple of ways. A simple way is, remember, right, and this goes back to my point, benzene is not a collection of three double bonds. It's not some kind of a triene, cyclohexatriene. And the evidence is the following. If I have an alkene, we know that if I were to treat that with bromine, what I'm going to get is trans addition of the halogen. Does that mean then that if I have benzene and I treated it, let's say, with one equivalent of bromine, would I then add the bromine across one of those and end up getting trans bromine? And the answer is no. In fact, you get no reaction. And that tells you right away there is something unusually stable about benzene, that it doesn't undergo that reaction, which a regular alkene, an alkene, I should say, not regular, but an alkene, undergoes very well. Another thing that we can do, and we've seen this type of experimental evidence for other things, is can we find a kind of reaction then that would allow us to tell how stable the benzene is relative to maybe what we expect. And then we realize, okay, we know from Orgo 1 that it's actually very difficult to take a benzene and hydrogenate it exhaustively with some kind of catalyst in order to end up getting cyclohexane. We know that this requires a catalyst. It normally requires high pressure and it normally requires temperature in order for us to do that. Nonetheless, the fact that the reaction requires a catalyst plus several hundred atmospheres pressure plus high temperature in and of itself should tell you that benzene is really stable. It doesn't want to be hydrogenated and converted to a cyclohexane, which we know is quite stable because it can adopt a chair conformation. So that in and of itself right, gives you an idea of how stable benzene is. But we can make it happen. What we can do is we can do one of these experiments where we hydrogenate and calculate the delta H, and then that should give us an idea. Now, rather than me drawing this out, I'll just take, go ahead and take a screenshot here of a graph from the textbook. So here's the thing. If we have here cyclohexene, we hydrogenated one equivalent of hydrogen gas, we find that we end up getting cyclohexane, and that releases 120 kilojoules per mole. So it looks like hydrogenating a double bond in cyclohexene releases 120 kilojoules per mole of energy. If I then take and I do 1,3-cyclohexadiene, two double bonds, how much would you expect? Well, you would expect twice 120, right? You would expect here, I would say that what I would expect here would be 2 times minus 120 kilojoules per mole. So I would expect 240. Instead, I get 232 given up, less than the 240. Now, a quick question I can ask you is, think about it. Why would it be less than the 240? Think about this, and you can tell me in class. Now, if I now have benzene, which has 3 double bonds, and I hydrogenate all 3 of them with 3 equivalent, right? You would expect this minus 120 times 3, which is 360. Instead, what you actually get is 208. In fact, less than what you give off when you hydrogenate 1,3-cyclohexadiene. So this is really far less energy being given off. It means that your benzene had a much lower energy content than you would have expected. How much? You see the difference here, 152. So that tells you how stable benzene happens to be. Because remember, all of these three things that are being hydrogenated, the cyclohexene here, the cyclohexadiene here, and the benzene here, all of them end up at the same molecule, the cyclohexane, so they end up at the same energy level. The more energy you give off, the higher the energy content of the original molecule. So the fact that you get only 208 kilojoules per mole being given off with benzene, when to do it for one regular alkene is 120, shows you that the benzene was in a much lower energy state, which means it was far more stable. This difference here between what was expected and what you actually got is the amount of stability that the benzene really has. It's a good measure of the stability. And that is what we refer to as aromaticity. We say that the benzene ring is aromatic, right? So good question here then is, well, why is it that benzene is so stable? Well, we go back to molecular orbital theory. So if I have a benzene ring, right, that has, let's say, double bond here, double bond there, and double bond there. So we have 6 carbons that are bringing 1 electron in an unhybridized p orbital, and they're trying to overlap. So MO theory, we treat this mathematically. We treat the wave, we treat the electrons that are coming to try to form the bonds, we treat them as waves, and we treat this mathematically. So that means then that what I have then is I start off here with 6 carbons, each bringing a 2p electron to the game, right? 2p in every single case. When they overlap in that ring, what are the ways in which the overlap can happen? Well, the best case scenario is going to be this one, where every wave is going to match in amplitude. So therefore, I have this double bond, 2 electrons here. I have that double bond, 2 electrons here, and I have that double bond, 2 electrons there. And because those waves are all perfectly parallel to each other, what it means is that those electrons can flow through the entire ring. And the way a lot of textbooks, I believe even the Klein refers to this, is that it's a closed shell electron configuration. That is a very stable arrangement. There are no nodes. The second most stable arrangement would be 2 of them that are equivalent in energy. I can have this case where these, let me draw so I'm not, so it's clear, a little bit clearer without scratches. All right, so I can have 2 that are the same energy level. So this one would be these 3 carbons would have their amplitudes, their orbitals match, but then these would match, but down here, which means there is a node right here where there is a mismatch. And if there's one node, that gives that arrangement less stability than when you have 0 nodes, as in the first case. Then you can have this arrangement where these 2 actually match, and we can have these 2 that actually match, but right here, there is a mismatch, right? These are down. So that means that what I have in that case is that your node falls right where they are. So it's easier to show this like this. Take away these, right? So I have to redraw it because I can't work in reverse. All right. So what we have here is these match and these match. And what we say is the node happens to fall right on top. So it's easier to just show it that way. Then we can have these two molecular orbitals that are equivalent in energy, what we call degenerate in chemistry. Let me redraw that because that's ugly. Like that. And now these are going to have two nodes. So how are you going to have those nodes? So here, what you're going to get is a case like this one, where we can say these orbitals for those two carbons match. We can say these also match. And then here, there's a mismatch. There's a mismatch. So I think I was giving you the wrong one for this third one down here. So kind of. Here, what happens then is that the node is wherever you have a mismatch, and there's a mismatch right here coming straight down right there, and there's a mismatch right here going in that direction. So I have two nodes now, which is even less stable. And then I can have this situation where right here, I'm going to have a mismatch. And right here, I'm also going to have a mismatch. You put it the other way instead. I'm going to have like that. So in this case, where do we see the nodes? Well, you notice that there's a mismatch right here, and there is a mismatch right here. So two nodes. And then the worst case is where none of the orbitals is going to match. So you see this here, where this one does match that one, which doesn't match this one, which doesn't match that one, which doesn't match this one, which doesn't match that one. And so now it's not two nodes, it's three nodes. You clearly see no matching here. You clearly see no matching this way, and you see no matching that way. So remember, each of these now represents, so the 6 atomic orbitals of these six carbons that are in the ring are trying to form a bond, right? So it's the waves that are coming together, and they can, of course, undergo constructive interference or destructive interference. Constructive interference is when they match and you get bond. Destructive interference is when the amplitudes don't match, you don't get any bond. So I have 6 atomic orbitals here that are trying to do this bonding. In MO theory, then, what we say is each of these represents a molecular orbital. So we can put them, start from down here. Let's say here, and then we have these two, then we have these two, and we finally have, let me make this a little bit smaller so you can see all of them. And then you have the last one, which is here. These are now molecular orbitals. There are 6 electrons. Following the system we have to use to fill electrons, we know 1, 2 here, 3, 4, 5, and 6. So these are, of course, what we call our bonding molecular orbitals, and these are what we call our anti-bonding molecular orbitals. The point here is the 3 bonding molecular orbitals contain the 6 electrons, which are now lower in energy, because right here is the energy level of the atomic orbitals. So you notice clearly the bonding molecular orbitals are lower in energy, which is more stable. So the electrons go into molecular orbitals that are lower in energy and therefore more stable. None of them are in the antibonding molecular orbitals, which would make it less stable. And what you want to focus on is the fact that right here you have this especially stable arrangement where there's complete matching, right? So you get constructive interference for all of the carbon orbitals, and that allows the electrons to essentially circulate throughout the ring. Remember, by now you know that if you can delocalize electrons, that is a more stable arrangement, because then the charges that go with the electrons are spread out over a larger surface area. So rather than the 2 electrons forming a pi bond being localized, they are now spread over the entire ring, and that makes that very, very, very stable. So that really is the reason for the really unusual stability of benzene, and refer to that as aromaticity. So then the larger question becomes, well, okay, benzene is aromatic, but if we are presented with other molecules and asked to make a choice, how would we know if the molecule happens to be aromatic or not? So there are certain criteria for aromaticity. Number 1, the molecule has to be cyclic. Number 2, the molecule has to be planar or flat. Number 3, you must have the ring must be fully conjugated. The electrons, right, must be fully conjugated around the ring. And number 4, they must satisfy what is called Huckel's number. And Huckel's number means that it has to satisfy the formula 4n plus 2, where n just means I can try 0 or 1 or 2 or 3 and so on, any whole number integer beginning with 0. So for example, if we take benzene, here is benzene. Is this cyclic? Yes. Is it planar? Every carbon on the ring is sp2 hybridized and therefore planar, and if they're all connected to each other, the whole ring must be planar. Is it fully conjugated? Are the electrons involved in the ring bonding fully conjugated? Yes, that is what we just saw. We saw that in the case of benzene, here we have 2 electrons for that pi bond, 2 electrons for that pi bond, 2 electrons for that pi bond, and because the ring is completely flat and those orbitals are parallel, the electrons flow completely over the ring, so they are fully conjugated. Question is finally, how many electrons does the benzene ring have? Well, we know that it's 3 double bonds that are involved. Each one has 2 pi electrons, so therefore this is a 6 electron system. Is 6 a Huckel number? All right, let's try 0. What is 4 times 0 plus 2? That is 2, right? We still haven't reached 6. So what is 4 times 1, the next number, plus 2? That is 6. 6 is a Huckel number, and therefore that is why benzene happens to be aromatic. Now, let us look at something that at first glance might seem to be aromatic. That would be if we have this molecule. Question, is it cyclic? Yes. Is it planar? Every carbon on the ring is sp2 hybridized and they're connected together, should be flat. Are the electrons fully conjugated? Sure, because here, I'll draw it this way because it's easier to show this way. If I have 2 electrons here and a double bond, 2 electrons here and a double bond, And since the orbitals are perfectly parallel, what it means is those electrons free flow throughout the ring, so it is fully conjugated. And finally, do the electrons involved in the ring satisfy Huckel's number? Well, how many electrons are we talking about? Two double bonds, which means two electrons for each double bond, 2 pi electrons, so that is a 4 electron system. So remember, when n is 0, the number would be 2. When 4 is 1, the number would be 6. So 4 is not a Huckel number, so therefore this is not aromatic. This is not an aromatic ring. Now, suppose I had, let's say, a ring like this one. All right. Is it a cyclic molecule? Yes. Is it fully planar? And there the answer is no, because here you have an sp3 hybridized carbon. That sp3 hybridized carbon is tetrahedral. If it is tetrahedral, it does not allow the 4 electrons that we have here and here to flow throughout the ring. So it's not fully conjugate, it's not planar. And if it's not planar, those electrons can't be fully conjugated. So therefore, this is not an aromatic ring. We don't even have to calculate if it fits Huckel's number because it's already failed an earlier test. Now, a question here might be, well, why? I mean, why is that? Why is it? How do you explain this Huckel number requirement? Well, one way of doing this is by invoking what's called Frost circle. So Frost is a chemist, I think he still works at Northwestern, who developed this way to explain really what's happening and to make it a lot quicker for us to be able to tell if a given ring system happens to be aromatic or not. Now, before I do that, I do want to emphasize something here. Notice the difference between these two systems that we have here. Notice that in the first case, the only test that this failed is the last one, is here. But it was cyclic, planar, and fully conjugated. But notice that this second one that we worked here, this one failed even before, right? So it failed the planarity test. We didn't even have to get to calculating Huckel's number. So there has to be a difference between those two systems. And what we say is, if the molecule satisfies the first 3 criteria that I laid out, but only fails the Huckel's number, we say that that molecule is anti-aromatic, which means that that molecule is very, very, very unstable, as opposed to if it fails one of the first 3 criteria, then we say the molecule is non-aromatic. Both cases are not aromatic, but we specifically label the second one non-aromatic and the first one anti-aromatic, and that is the difference. Again, for a molecule to be anti-aromatic, it satisfies the first 3 criteria, but fails only the last one, which is the number. For a molecule to be non-aromatic, it fails one of the first 3. It's either not cyclic, not planar, not fully conjugated. And you find that most textbooks will actually say it's 2 criteria, cyclic and then planar and fully conjugated, because they go hand in hand. But there are a couple of cases where they don't necessarily go hand in hand, which is why I divide it into 3. But if the molecule fails one of those 3, then it's non-aromatic. It's not anti-aromatic. And a non-aromatic molecule is actually more stable than an anti-aromatic molecule. So what is Frost's? In fact, let me do one more here to illustrate this point, because it's a curious one you have to know. If I have the following molecule, right? Cyclooctatetraene. Is this molecule cyclic? Yes. Is this molecule planar? Well, I look at every carbon that I have here, and every single carbon is sp2 hybridized, much like when we have benzene, you see that every carbon is sp2 hybridized, and so we say that if every carbon is sp2 hybridized and they're all connected and they're all planar, the molecule is planar. Turns out this one is not planar. So it fails one of the first three, so therefore this makes it non-aromatic. And if you're saying, but hold on, why? Turns out, if you have, right, if you think about this, if you have that molecule being flat, then all of the orbitals are perfectly parallel, and that's why the electrons are flow throughout the ring, and you see the system is fully conjugated. However, this cyclooctatetraene adopts the following um, geometry, so to speak, the following structure. It actually does this bit. This is how it sets itself up, like that. So I have one double bond here, one double bond there. But then I have these double bonds here and here, and these double bonds here and here. Once that, so that means these that I have here are on the same plane, but the ones that I have in not blue but the other color are now higher, right? It's like a boat, right? It's has this kind of a shape. So these up here are not on the same plane as these down here. So therefore, they're not perfectly parallel. And if they're not perfectly parallel, that means that in this system, the electrons can't flow throughout the ring. So it's not planar, it's not fully conjugated, right? And this one you have to remember, the cyclooctatetraene, they expect that you know this particular arrangement. So getting back to the point of Frost's circle. So what Frost says is, okay, when we look at benzene, and you will recall the MO diagram that I set up, I had the lowest one, two higher ones, those are my three bonding, and then these are my three anti-bonding, right? And we said that I had two electrons here, and two here, and two here. So when I look at the highest occupied orbital, it would be these two, you notice that every electron is paired, and this again is what's referred to as a closed shell electron configuration. So Frost says, we can actually do this very quickly by doing a Frost circle, right, named after him. So the Frost circle says, I draw a circle, and then I put my molecule in question. So I'll read it out so you get this. It says, inscribe a polygon, which is the ring in question, making sure that one of the connecting points is at the bottom of the circle. So for my benzene ring, I would have to do it this way. So you notice that one of the points is down here by itself. In other words, we cannot do it this way. You cannot draw this ring this way. Like that, because in this case, notice that what I have is two of them are down here at the lowest level. We have to have just one. And then wherever the ring touches the polygon touches the circle, we draw one of these, and that represents a molecular orbital. So therefore, when I look at that, right, just redraw it, I have a lower one, two equivalent and higher, two equivalent and higher, and the highest one, which is exactly what we saw here. And we have, again, the highest occupied orbital with everything paired. And that is a stable arrangement. And that is why we end up getting that molecule being aromatic. But now consider if I have this molecule. So if I draw my circle, then I would draw the polygon this way to ensure that I have one of the points at the bottom. So I have here, 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 and here is where the polygon touches the circle. So my arrangement is one low, two higher, and one up there. Remember, 4-electron system. 1, 2, 3, 4. Sorry, 1, 2, 3, 4 there. So therefore, what you see is that the highest occupied orbital doesn't look the same as above, whereas above, the closed shell system has, noticed the orbitals with 2 electrons paired. Here, they happen to be single. And what do we know when electrons are single? It's not as stable as when they're paired, so they're very reactive. In a sense, that's like a diradical. It's very reactive. It's not stable. It wants to get to a situation where it will pair off and therefore become more stable. And therefore, this molecule is not going to be aromatic. It's very unstable, and therefore, it's going to be anti-aromatic. It's not going to be aromatic, and we already know why we would classify this as anti-aromatic. So this is what you do with Frost circle. And in fact, I tell students we don't even have to get into drawing the whole circle, etc. You can more or less, how do I explain this? Here's how I'll do it. I look at that and I'll say, okay, here's my lowest one, which will end up touching the bottom if I moved it around and put it that way. That means these two would be equivalent and touch the circle. These two would be higher and equivalent and touch the circle. These two would be higher and equivalent and touch the circle. And this one would be the highest one. So therefore, let me just rewrite it in a more vertical orientation. So here is my first one, which is the lowest one. Then I have two here that are higher and equivalent. So I'd say here and here. Then I have two more that are higher and equivalent. So I'll say here and here. Then I have two more that are higher and equivalent. So I'd say here and here. And I have a final one up here that's by itself and higher. So it's up here. So therefore, let me make sure I put that little line here so we're dealing with different things. How many electrons does, sorry, I forgot to put that you have double bonds here, 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 and here. 4 double bonds means I have 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. And again, you see the unstable arrangement where, right, they're single and therefore not stable. It's not a closed shell system, so it's not going to be aromatic. Now notice the difference. In the case here, both of these cases, we say they are not aromatic, but we know that this one is anti-aromatic because it only fails the last criterion, whereas we know that this one is non-aromatic because it is not planar. It fails one of the first 3 criteria. So both are not aromatic. The first one is anti-aromatic. The second one is non-aromatic. So just so we're clear. And if you look at the textbook, you see this figure. It just gives you an idea how you're supposed to go doing that. And they do point out something that I don't like when people memorize things, but sometimes it does help make things go fast. Here is something to note, right? The number of bonding orbitals is always an odd number. Aromatic compounds will always have an odd number of electron pairs. So if you have an odd number of electron pairs, it's going to be aromatic. That's one quick way to make life shorter here. But that is Frost circle then explains why you get the criteria that we actually said. Now, you can keep going with this. And for example, then, so these molecules are really all considered to be, they're called annulines. So let me just point out and clarify what this term is. So when we're talking about annulines, it's just when the molecule is a single ring and it contains a fully conjugated pi system. So for example, benzene would be considered an annuline because it is a ring, single ring, that has a fully conjugated pi system. So as an annuline, you refer to this as 6-annuline. Why? Because there are 6 electrons, right? So then I can have this one where I would have double bonds at these positions. So now, is it cyclic? Yes. Is it planar? Well, every carbon on the ring is sp2 hybridized and they are connected. So that would suggest yes. Yes. Is it fully conjugated? Sure, because notice that you have perfectly alternating double, single, double, single, double, single, double, single, double, single, and I'm back where I started. So therefore, that must be fully conjugated. So it's cyclic, planar, fully conjugated. How many electrons are we talking about here? Well, we have 1, 2, 3, 4, 5. 5 double bonds. 5 times 2 is 10. So this is a 10 electron system. Is that a Huckel number? Well, when n is 2, 4 times 2 is 8 plus 2 is 10. So therefore, you would say this molecule is aromatic. And you'd be totally wrong because there is something here. See this hydrogen that's pointing inside the ring? And this hydrogen that's pointing inside the ring, meaning these hydrogens out here are pointing outside the ring, right? And then you have those that I highlighted down there, right? So let me see if I can erase just the... Right. So now let me emphasize these 2 electrons that are pointing inside. The problem with them is that they are on top of each other, and that creates a problem. So the solution to that is, even though it's one ring, you can think of 2 halves. And so rather than the ring being like that, one half of the ring moves out of planarity. So they're not like this, but instead one is like this and the other one is like that, or shown this way. Instead of them being like that, one is like that to avoid those 2 hydrogens being on top of each other. So that ring is not planar. And if it's not planar, it's not fully conjugated. That makes that a non-aromatic ring. Once the rings become bigger, even when you might have a bit of that, and by the way, just since that's 10 electrons, just to remind you, we would refer to this system as a 10 annuline. Then you have this one, which is bigger. It is 14 annuline, and it looks like this. I have here, here, there. Okay, double bonds here, 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 and here. Cyclic, yes. Planar, well, you might say, aren't we going to suffer from the same thing where I might have that H, that H too close to each other, this H and that H too close to each other. So notice that I have 7 double bonds there. So therefore, this is a 14 annuline. And yes, it turns out that those hydrogens that are inside, they do create some steric issues, but now the ring is big enough that it actually deviates only very, very, very slightly from planarity, unlike 10 annuline, where the one half of the ring really has to deviate from planarity. In the case of the 14 annuline, the deviation from planarity is so slight that just a slight little deviation makes those hydrogens now fit perfectly, and therefore that is an aromatic ring, right? So that is something to keep in mind. Now, can you have, remember I talked about heteroarenes. I used that term before in the first video when I was showing you examples of aromatic rings, but we had something other than a carbon in the ring. So can you have heteroarene? And the answer is yes. So for example, if I have this molecule, it looks very much like benzene, except a nitrogen has taken the place of the carbon. Now the question here becomes, does this electron pair get involved in the ring bonding? If it does, that now becomes 8 electrons, and 8 is not a Huckel number. But if it is not involved, if the lone pair is not involved, and only the pi electrons are involved in ring bonding, then 3 pi bonds means 3 times 2 is 6. 6 is a Huckel number, and therefore that would be aromatic, right? We also have one like this, closely related, where instead of one, I have 2 nitrogens like this, and I have double bond, double bond, double bond. The question is, okay, that looks just like benzene, you would say aromatic, but what about these 2 electrons on that nitrogen and those 2 electrons on that nitrogen? Are they involved, both pairs or one pair? And you see, we could have here potentially 6, 8, or 10 electrons. 6 is a Huckel number, 10 is a Huckel number, 8 is not. And then we have the 5 membered rings, which would be something like this. And then we have this one with 2 electrons, very similar to the other 2 systems where one has 2 and one has 1 electron. So something like this, where I have double bond here, a pair of electrons here, and a pair of electrons there. The question is, what about these lone pairs of electrons? Are they actually involved? So this one is pyridine. This one is pyrimidine. This one is pyrrole. And the last one is imidazole. So are they aromatic or are they not aromatic? Well, if we do a quick analysis like we did for benzene, we can see the following, right? When we do the MO diagrams in a sense. So for this one, I'll draw it this way, nitrogen here. So notice that you have a nitrogen to a neighboring carbon double bond, a carbon to carbon double bond, and a carbon to carbon double bond. So what about the lone pair of electrons? Well, here's the thing. In a universe, 2 objects cannot occupy the same volume of space. So therefore, the orbital with the 2 non-bonding electrons cannot be up and down here on the nitrogen, because that's already taken by that electron that is involved in pi bond formation with a neighboring carbon, which means that those 2 electrons have to be perpendicular to the plane of the ring, and they're out here. They're not participating in ring bonding, which means that 2 electrons here, 2 electrons here, 2 electrons here, and since everything is parallel, these can flow freely throughout the ring. That makes that cyclic planar fully conjugated 6 electrons, so that is aromatic. And you see for this one, it's essentially going to be the exact same situation, except I have 2 nitrogens. So this time, again, I have a nitrogen to carbon double bond, a carbon to carbon double bond, and another nitrogen to carbon double bond here, which means that in each case, the lone pair is not involved in ring bonding. It's out there, right? perpendicular to the plane of the ring, and therefore I have complete delocalization here. So that makes it cyclic planar fully conjugated and 6 electrons, which is a Huckel number. So therefore that is an aromatic ring. Then I can look at pyrrole and ask, well, what about that one? So if we draw out the system for pyrrole, here's what we would say. So there is a carbon to carbon double bond. There is a second carbon to carbon double bond. Those are perfectly parallel, so the electrons flow throughout. Now notice the nitrogen here in pyrrole has a lone pair and a hydrogen. One of them has to set itself up, one orbital will set itself up parallel to these 4 that we already have, and one perpendicular. And what happens is the orbital with the lone pair sets itself up that way so that it's parallel, right? So in other words, it's up and down. And therefore, the nitrogen to hydrogen bond is out here perpendicular to that plane, and it's not involved in anything with the ring, which means then that because this orbital that has the 2 electrons on the nitrogen is parallel to the 4 that we have in the ring, those 2 electrons can flow freely that way, and the 4 pi electrons can flow freely throughout. So this is again a 6 electron system. So really, this is cyclic planar fully conjugated and 6 electrons, which is a Huckel number. And you can see where the other one, imidazole, is going to be the same. Now, one thing that I tell students is there's a quick way in which we can show that pyrrole and imidazole are actually flat, because usually students will say, hold on, but that nitrogen is not forming any double bond. So it's not sp2 hybridized, it's forming all single bonds, so it's sp3 hybridized, which means then that it's tetrahedral, and that means that molecule is not planar. So what I'm going to do is show you the following. So here, let me draw it down here where it's bigger. Okay, so I have this. I have double bond, and here. I can take this lone pair, form a resonance structure like this. In which case, the nitrogen now has a double bond there, and you can clearly see it's sp2 nature. Here, you have that. So you see the nitrogen is sp2 hybridized. So you can look at it that way, and therefore I have 2, 4, 6 electrons, or you can do the analysis on the basis of the orbitals, which is what I've done here to prove the exact same thing. So yes, you can have heteroaromatic molecules, no problem. Finally, one thing to ask is, well, what if I had something like this, let's say? What if I had a molecule like or if I had a molecule like this one, or if I had a molecule, let's say like this one. And this, and I had double bonds here, 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 and here. Are these aromatic? These 3 molecules fall into a class of molecules that are called polycyclic aromatic hydrocarbons. All right, and the name gives it away, aromatics. For short, they're called PAHs. Very interesting set of molecules because many of them are known, a lot of them are suspected carcinogens, and there are sources continually of these things. And as we get exposed to these, there's a problem of cancer. Now, technically speaking, only single ring molecules can be aromatic. But you know the old saying, if it looks like a duck and it walks like a duck and it quacks like a duck and it swims like a duck, it's probably a duck. And these things, PAHs, behave exactly like benzene, so therefore they are aromatic. And in fact, if you look at this system, right, all of the carbons are sp2 hybridized, so cyclic planar, fully conjugated. How many electrons? Well, there we have 5 double bonds, 10 electrons, 4 times 3 is 8 plus 2 is 10, so that explains that. Then we have the second one, 2, 4, 6, 8, 10, 12, 14. 4 times 3 is 12 plus 2 is 14, so that makes that a Huckel number. And then here we have 2, 4, 6, 8, 10, 12, 14. Again, 14 is a Huckel number, cyclic planar, fully conjugated. So these are aromatic molecules, right? So hopefully from home or in class, extra, and so on, you will be able to look at a molecule and decide if that molecule is aromatic or not. And I'll end this video by saying it's important that you understand aromaticity because aromaticity allows you to explain things. We can invoke aromaticity to explain things. Perhaps the classic case of this would be a question like this. You can be asked, right? I have 2 hydrogens here versus, let's say, this molecule, which also has 2 hydrogen. The question here might be, which molecule is more acidic? Which is a way of asking. Another way I could ask is the pKa of these protons higher or lower? Is the pKa of these protons higher or lower than the other one? In other words, another way is, in which case will the pKa of the protons highlighted be lower? Which is the same as asking, which one is a stronger acid? So you look at that, and what you would say is, in each of these cases, the molecule is non-aromatic because the carbon that I've highlighted with the 2 hydrogens is sp3 hybridized. So therefore, that molecule is not planar. Failed that test. It's non-aromatic. Now, which one is a stronger acid? Well, let's consider what happens if a base comes in, and these act as acids by donating a proton. So the base grabs a proton and kicks the 2 electrons into that carbon, which means that the product that I'm going to get from this molecule acting like an acid is this carbon now has a minus charge and 2 electrons. So if the base does the same thing here, same situation, I now have this, where this carbon has a 2 electrons and a minus charge, which we draw this one so it looks the same. It has 2 electrons and a minus charge. Now here is the thing. Now I can look at this molecule and I can see, right? And I'll draw it this way. So here I have my carbon to carbon double bond. Here I have my carbon to carbon double bond. They're perfectly parallel, so the electrons flow freely. What about the carbon with the 2 electrons and the minus charge? Well, the 2 electrons and the minus charge set themselves up like that, perfectly parallel to those. I'll take off the minus charge just so that it doesn't look like I'm doing something else. And therefore, those electrons can flow freely, and the electrons from here can flow freely that way. So that means it's cyclic planar, fully conjugated, and 6 electrons. So that means this molecule is aromatic. The same argument there would therefore make this one cyclic planar, fully conjugated, but 2, 4, 6, 8 electrons. So it fails the Huckel number. Therefore, this becomes anti-aromatic. So here is the question. Which one is a stronger acid? Well, when this one acts as an acid, the product is an aromatic product. When this one acts as an acid, the product is an anti-aromatic. Well, why would this second one give up a proton and then go from a non-aromatic to an anti-aromatic, which is less stable? Energetically, that is not favorable. Whereas going from a non-aromatic ring to an aromatic ring means I'm increasing stability. That is thermodynamically favorable. So the first one will more readily lose its proton, act as an acid, lose its proton, because the resulting molecule that you get by losing a proton is a more stable aromatic ring. So see there, we've invoked aromaticity to explain an observation, right? And you will see where we can invoke aromaticity for more things, right? So I'll end this video right at this point. We'll take it